using that Blue Ridge hot tub problem. The very first example we talk about in this class. We implement the model, solved it, and we got the solver solution. Okay. Based on this Excel spreadsheet, what are you going to suggest to the manager at the Blue Ridge hot tub company? You guys still remember the problem? What's the suggestion to them? Okay. Okay, so make 122 aqueous bus and 78 hydrolysis, right? So that's the suggestion. And what is this suggestion based on? All of those information here, right? The unit profits of aqueous bus should remain to be 350, and hydrolysis should remain to be 300. Same as the labor constraint, pump constraint, tubing constraint. Okay, and if you work in the company, only give this, okay, we should make this many to the manager. Probably that's not a good enough report. Okay, managers always want to know what if. Okay, so then when, okay, the unit profit, say if we are going to, are we able to say like increase the profit a little bit because the market is really good recently. We are sure if we increase the profit, we're still going to sell the same amount. I mean, sell all of them. So what should the new decision? Should we make the same numbers of each type, or those numbers should be changed? Okay. Or say this company trying to implement some improvement to their manufacturing, and so they implement the lean manufacturing and save some resources, and say the labor part gets really increased, so they now use less labor. Okay, so what does that mean to this decision? Are they going to make the same amount? Okay. Or say, okay, they found, oh, we didn't count some of the extra labor available. Here, the labor is really one of the constraints that prevents the solution to improve, right? So if we have more labor, should we make the same amount as you suggested? Okay, so those are all the questions that the management would like to know. Okay, and what do? Do you go to, okay, solve it again when the question comes, or can you prepare a comprehensive report giving all those different scenarios to the manager? Say, okay, here are the range. Say, okay, for the hydrolysis, as long as your profit is between 250 to 350, you're going to make the this many aqueous bus and hydrolysis. The number won't change. Okay. And here are those available of the resources. As long as those resources change within this range, our profit will still be the same. But the number to make probably will change. Okay. So that's what the sensitivity analysis is going to tell you. And when solve as we said, when solving LP models, we assume that all the values associated with those coefficients, they remain to be the same, and they are known with certainty. But such certainty never exists, and things are always changing. No. Sensitivity analysis will help ask questions, say like, okay, how sensitive the current optimal solution is to changes to those various coefficients in the model. Okay, and remember we said this is the general format of an LP model. Okay, so the objective function with those coefficients being noted as we see, and the constraints, left-hand side constraint coefficient A, and right-hand side with B to represent. Okay, we're going to study how sensitive is the solution, which means the x1, x2 value. Okay, and we'll look at also how sensitive the objective function value will change when changes to C, A, B happen. Okay, so some approaches to sensitivity analysis, I would say just to change those coefficients and resolve it again, rerun the solver. That's one way. Sometimes it's the only practical way to do it, especially if you want to know a certain scenario in which multiple coefficients change. Okay, sensitivity analysis report is very powerful, but not that powerful. That tells you everything. Okay, but another way is to do the graphical analysis. Like in chapter 2, we talk about how those changes. Okay, we'll mention that. And by using the graphical analysis, we'll be able to see how the feasible region change, how the level curve change, how the optimal solution change. So that's one way. But with that, it only works with how many decision variables? Graphical solution. 2 variables. Okay. Third, mathematical deduction. Because the A, B, C's are all related, and we know that how the optimal, just think that, like for example, the level curve is decided by what? Level curve slope. What decides the level curve? What value? The objective function values, objective functions coefficients, right? So for that part, we should be able to calculate using mathematical deduction how much those values can change without changing the optimal solution. And fortunately, we don't have to do that by hand because solver produced this sensitivity analysis report for us. Okay, once again, we'll use this example. Model already opened here. Okay, so that's the model that we implemented in solver. So you probably have noticed then when you go to solve the problem, you read this message and say, oh, click OK. And on the right hand side, there are some reports that you can look. Okay, you just click on all of them. Just click OK. Then you will see all of the report got generated for this model. Okay. And one thing I want to notice that, let's click on one of them. You see that in this sensitivity report, the name of the cell, for example, C13. Okay, C13, which is this one. Okay, that's our objective function. Remember that? Okay. It says, okay, the name is total profit. It put the equals bus here. That's because the row label is total profit, and the column label, it took this equals bus here, which is not very accurate in the sensitivity report, but we know that we know this is the total profit part. Okay, and for example here, this one is pretty meaningful here. Number to make equals bus 122. Okay, and that came from here. So number to make equals bus. So when sensitivity analysis report is generated, it automatically take the row number, the row label and the column label, put them together to be the name of that specific cell. That's an indication of the importance of having meaningful label for all your cells, especially consider the column and the row, because a sensitivity report with those names, it's much easier for you to interpret it. Okay, if your name will be like X12, just some like a number to make, then you don't know which one is weight, or even just say like say equals bus hydrolysis. It's not very meaningful. Okay, so that's just one point that I want to point out, especially in the homework assignment. Those problems are, say you need to first formulate the problem. Okay, maybe many of the business problem, and then you interpret the sensitivity analysis report by answering. Okay, say if the resource of labor increase that many, what does that mean? So you need to find, okay, which cell represents that labor of the labor resource part. If you don't have meaningful labor for your cells in the Excel model, it will be very difficult for you to find out which way is which. Okay, so that's very important. Now let's look at how to interpret those First, we generated 3 reports. The first one generated is the answer report. So this one does not give much information. When it gives like, okay, what's the total profit and what's the final value of your decision variables. Okay, and for the constraints, only thing I want to notice is the constraint part. Okay, I'll ask you guys to look at this column and this column. Now tell me, what do you see here? What's the relationship between the status and the slack? Look at this. Okay, which one uses all of them? Right, labor, pump and labor. Remember, those 2 resources are all used up, right? And the tubing is not used up. Okay, so you can see that the 2, and we remember that the graphical solution is here, right? And that's where the pump and the labor intersect. Okay, so these 2 constraints, they are binding and they have a slack of 0. Okay, and this slack means no more left, as it tells by the name, right? No more left, no slack. And this tubing part is not binding because it has 168 left. Let's go back to the Blue Ridge Hub here, tubing. What's the difference between these 2? 168. Okay, so that's what this slack is. Okay, so what is slack? Slack equals to be the difference between, I'll put absolute value, left hand side value subtract right hand side value. Okay, so that's the slack. And binding constraint. So binding constraint. Constraint always have 0 slack. And the non-binding, slack is not 0. It's always non-zero. Okay, so that's what I want to talk about for this answer report. Just pointing out if it's a binding constraint, then the slack. Okay, then this part is what we're going to focus on for this. Okay, so this sensitivity analysis report we're going to look at. So this first part is the same as the answer report. It just tells you like what's the objective function value. Okay, so then we'll look at this adjustable cell part and the constraint set part. So what it answers, the questions that the sensitivity analysis report answers, the amount by which the objective function coefficients can change without changing the optimal solution, which means the x1, x2 values. Okay. The impact on the optimal objective function value of changes in constrained resources. So as I said, if say we have more labor, if we have more tubing, if we have more other pumps, what impact will be on our objective function value. Okay, that's the total profit. It's not the x1, x2 value. That's something to differentiate. Third, impact on the optimal objective function value of forced changes in decision variables. Say a decision variable result is 0. Say in the Blue Ridge hot tub, if one of them is 0, that means we're not going to produce any of that hot tub. What if the company says, okay, just for strategic reason, we want to produce this, even though it's not going to make more money for us. We just want to develop this new product. how much impact will that on our total profit. Sensitivity analysis will tell you. And impact changes in constraint coefficients will have an optimal solution. Okay, so we'll talk about the first one, objective function coefficients. So if we look at the graphical solution, okay, we said that the objective function coefficient is related to the slope of this level curve, right? Okay, and currently this is the, this is the current optimal solution, okay? And that's because of this slope. If the slope changes to like this, then the optimal solution is which point? This bottom corner point, right? Okay. And or if the slope is really flat, if it's really flat like this, then this point will be the optimal solution. We have to move to this direction. Okay. So you know that, so you see that this slope, which is determined by the coefficient, really determines which point is the optimal solution. And from this point to this point, there is some space for it to change. Okay, so let me go to this graphical representation here. Sorry, those arrows are really blocking some of those values here. But so originally, this is the point. Okay, so let's see. Let's just put the 440 here. 450. Okay. So when it changed from 350 to 450, the optimal solution changed from this one point to this entire line. And then we talk about that, that's alternative solution, right? And if you change it to one more point, 451, then the optimal solution changed to here. And you see that we changed it from all the way from 350 to 450 until this point and the entire line becomes the optimal solution. Okay, that means there is a range, which is how much? 350 to 450, 100. So that's this allowable increase of 100 units that this coefficient can increase without changing our optimal solution. Okay, and it's the same for this part, and want to do it here. So you use this slide to illustrate that. So that's what we have, the original objective function, and the optimal solution is here, and this blue dotted line is the level curve. And when we change it this way, this time I changed this x2 value from 300 to 200. It also get changed to this point, so the optimal solution changed. Okay. So if we look at that, just now this is 100 and this is 100 too. Okay. So the values in the allowable increase and allowable decrease column for the changing cells indicate the amount by which an objective function coefficient can change without changing the optimal solution. Remember, optimal solution means that point. Okay, it's the decision variable's value. It's not the objective function value. Okay, it's the decision variable's value. Think about that. Let me ask you, will the objective function value change?
Yes.
Why?
Because the objective function is a function of the point that we're looking for.
Okay.
So as you're moving, when the amounts are, when the constant change.
Okay. Okay.
The value of the objective function.
Okay. Okay. So the objective function value is a function of those decision variables, which want to change in this case, and their coefficients, right? And since the coefficients change, object function value will change for sure. Okay, some common mistake students make before that they say, okay, that's the allowable increase decrease for the objective function value, and the solution to remain to be the same. It's not right because your coefficient changed. How come your objective function value does not change? Okay, it's only about the optimal solution, which means the decision variable values. Okay, so let's look at, let's go back to, I don't know whether you guys printed out that at one page. I asked you, so one thing you can do is use that one page to take notes. Similar as mine here. Oops. Okay, so let's write here. Okay. Okay, so what we talk about is here. So the adjustable cells represent those. The first one we're looking at are those ones. Okay, so the allowable increase and allowable decrease in the adjustable cells represent the amount by which those coefficients. So you can read this table as these are the allowable increase decrease of. Okay, so allowable increase and decrease of the objective function coefficients. Okay, for these ones to remain the same. Okay. These two columns are the allowable increase decrease of the coefficient, objective function coefficient, in order for the decision variable values to remain to be the same. Okay, so if you remember in this way, it's easy. What do these values represent? Okay, and then a special case. A 0 here means, okay, think about the graphical solution. In terms of, okay, what happens if there is a 0 here? What does that mean? When there is a 0 here, it means just one unit of change, the solution will change. Okay, so if you remember what happened here, 450. So at this point, you have alternatives because like all the points on this line are solutions, right? Just the one unit of change on either direction. Say, okay, now it's 450. If we change it to 449, the solution becomes this top point, right? Or if we change it to be 451, solution becomes this bottom point. What does that mean? When this objective function coefficient is at 450, the allowable increase or decrease of this coefficient is 0, because just one more unit of change will change your solution from all the points to this point or this point. Okay, so a 0 here indicates that currently you have alternative solutions. A 0 means if we represent it graphically, all the solutions on this point, on this line, are the solution. Okay, and just one unit of change will become this point or this point. Is this part clear? Okay. Now we go back to here. Okay, means alternate solution exist. Okay, so any 0 here means alternate solution exists. So that's what what this here slide means. Okay, and what we talked about earlier is only for one change in the coefficient. Okay, like for the 350 and the 300, only one of them change, and the allowable increase decrease is only applying in like just one change, and the other remain to be the same. Okay, because think about that, if you change both, then slope you may not know what happened to the slope. Okay, but there is a 100% rule to use if you want to determine whether the optimal solution will change when you change coefficients simultaneously. Okay, and there are two cases. Case 1, all variables with changed objective coefficients have non-zero reduced cost, or case 2 is with 1 0 cost. But both, so we'll look at this first case. First case, if all variables with changed coefficients have non-zero reduced cost. We'll talk about reduced cost later. There is a place to find the reduced cost. Okay, the current solution remain optimal if those changes are within the allowable increase or decrease. Okay, so that's an easy case. But the second case, if at least one variable with change objective coefficient has a reduced cost of 0, then you look at the percentage of the change of that, the percentage of the change in regard to that allowable increase or decrease, and you add them together. If the sum is less than or equal to 1, then you are sure that the optimal solution won't change. Otherwise, it's not guaranteed. It may still not change, but it's not guaranteed. Okay, I'll illustrate this here. So let's go back to our notes here. So for simultaneous change, for example, now the original objective function is this. Okay, and now we're going to change this one to be 340 x1 plus 310 x2. So this is simultaneous change, and we're going to use that 100% rule. And that 100% rule is to look at, okay, how much change has occurred. So this one, from 50 to 350 to 340, we decreased 10 units. Okay, so that's amount of change divided by allowable decrease plus that amount of change. In this case, we increased 10 units. So I put this increase. So it equals to be the 10 divided by, because the first case is a decrease, so we need to look at the allowable decrease of this coefficient. Okay, so allowable decrease is here, 50. Okay, divided by 50 plus, it happened to be 50 here too. In this case, it's allowable it's an increase, so it's a 10 unit divided by allowable increase. This case, you need to look at the increase. Okay, that's again 50. Okay, which is less than 100%. So solution won't change. Okay, so that's that 100% rule. Just make sure you identify whether the change is an increase or it's a decrease. Okay, if it's an increase, make sure you get that allowable increase value to be the denominator. If it's a decrease, then get the allowable decrease to be the denominator. Okay, and then we use absolute value. Yes?
So, what do you mean by the solution will not change? You mean
x1, x2 value won't change.
you mean only the variables?
Right. That's what solution means, right? Solution means the decision variable values. Okay. Okay, so that's about this table.